Hello everyone, so I have covered electrostatics in a single video and I have categorized numericals into problem types. So I've made your life super easy. So if you watch this video till very end, you have the idea about different types of questions going to be asked in JEE Mains. So let's see. First we will discuss weightage and then the syllabus and then mind maps. Then the previous year's questions which I have categorized as problem type. Now who will get benefited from this video? So if you have some basic knowledge but you are unable to approach the problem, then this video is for you. And you have done NCERT and you're pretty good with NCERT level concepts, but you want to write JEE Mains, but somehow you're facing problem in JEE Mains numerical. So this video is for you. And you have done some formal coaching, but still you want to improve problem solving skill. There is a gap in application of the concept. So this video is for you. Right, then how you can use this video effectively? So first, revise the short notes which you prepared for this chapter. Then write down the important information from the video. And if I give you a question, if I discuss a question, first you have to pause the video, pause the video, try to solve the question on your own. If you're still not able to solve the question, then you have to see the solution. Right, so first let us see the weightage. So there will be around 2 questions will come from electrostatics. I am not including capacitors here. It's a higher priority topic, so it is very important. And this is the syllabus. You can pause the video and just look at the syllabus. And this is the mind map where I have mentioned all topics and subtopics. Right. Right, so now let us start with the problem types. So very first problem type is Coulomb's law based on the formula. So let us see a question. Force between 2 point charges Q1 and Q2 placed in vacuum at r centimeter apart is F. So we have given 2 charges Q1 and Q2 and the distance between them is r. And they are exerting force on one another, and we know that in Coulomb's formula the force is always along the line joining the center of the 2 charges. So the force on the left charge will be in the left direction and the force on the right charge will be in the right direction. And we can say this force will be 1 upon 4 pi epsilon naught times Q1 Q2 upon r square. Now what we have done, the force between them when placed in medium having dielectric constant K, which is 5, and the distance is r by 5 centimeters will be, okay, so now what we have done, we have changed the medium, and we know that if we change the medium, the permittivity will change. So in the new medium, the permittivity will become K times epsilon naught, right? So that is the new permittivity. And now we have reduced the distance also. Now this distance has become r by 5. So we can say the new force will be 1 upon 4 pi K epsilon naught times Q1 Q2 divided by r by 5. And this can also be written as 5 square divided by K times F. Got it? And what is K? K is given as 5. So this will be 5 times F. So the new force experienced by the 2 charges will be 5 times the original force. So the right answer would be option 2. Let us see another illustration. 2 identical conducting sphere P and S with charge Q on each repel each other with a force 16 Newton. So Coulomb's law is applicable for point charges as well as for uniform spheres. So we have given 2 spheres and they have charge Q each, and let us say they have placed the center to center distances r, and we have given they are exerting a force on each other which is 60 newtons. A third identical uncharged conducting sphere R is successfully brought in contact with the two sphere. So now we are taking another sphere, identical sphere. Now this sphere first get in contact with the first one, and then it get in contact with the second one, and then we'll move this sphere away, right? So when we have identical sphere, the charge will be equally divided on both the sphere when we are touching them. So if we touch, let me name them. So let us, this is sphere 1, this is sphere 2, and this is sphere 3. Now if you touch 1 and 3, the charge on both the sphere will become q by 2, right? Now the sphere 3 has acquired q by 2 charge. Now we are touching sphere 3 and the sphere 2, so the total charge of the system is q by 2 plus q, and this charge will be equally divided on both the spheres, divided by 2, so that will be 3 by 4 q. So if I show the final charges on sphere 1 and 2, on this sphere it will be q by 2, on the second sphere it will be 3q by 4, and we are not changing the distance between them. So the new force will be k q by 2 times 3q by 4 divided by r square, and this will be 3 by 8 kq square by r square, right? And what is kq square by r square? That is the original force. So that is the original force. So the answer will be 3 by 8 times 16, so which is 6 Newton. So option 2 is the right answer. Now let us see the second problem type, where we have particle attached to the thread. So let us see this with this illustration. Two identical charged spheres are suspended by string of equal length, and the string makes an angle theta with each other. When suspended in water, the angle remains the same. If the density of the material of the sphere is 1.5 grams per cc, the dielectric constant of water. So we have to find the dielectric constant of water. Okay, let us see. So we have given two identical spheres which are suspended with the help of two identical strings, and the angle between the string is theta, and these two spheres, they are repelling each other away from they are repelling each other, and the force will be in this direction. So in such questions, what you have to do, first you have to draw the free body diagram of any charge. So let me take the first one, right? Let us say this left charge is charge 1 and the right charge is charge 2. So if you draw free body diagram, let us jot down all the forces acting on that. So there will be a gravitational force mg, and there will be a Coulomb repulsion, that will be, let me call it as F, and there will be a tension force away from the charge, right? Now this tension must be along the resultant of, must be opposite to the resultant of F and mg. So if this angle with the vertical is theta by 2, then this angle is also theta by 2. Now from this right angle triangle, we can say tan theta by 2 is equals to F divided by mg. Okay. Now what we have done, we have submerged the setup in water, and due to that, now the sphere will also experience buoyant force along with Coulomb repulsion. Now if we draw free body diagram again, so there will be a tension, let me call this as T prime, and there will be a weight which will be mg, and now there will be a buoyant force in the upward direction Fb, and there will be Coulomb repulsion, and Coulomb repulsion will decrease by a factor k, which is the dielectric constant, so F by k. So what we can say, this T prime will be opposite to the resultant of F by k, Fb and mg, And FB and mg are in the same direction, so we can say mg minus FB will be the net force in the downward direction if we add up these two forces, right? So we can show this as mg minus FB, and there will be F by K in this direction, and this will be T prime. And we have given that the angle between the string is not changing, so this angle will be theta by 2 only. So we can say T prime, not T prime, sorry, it will be tan theta by 2 will be F by K divided by mg minus FB. Okay, now this is the first equation, this is the second equation. Now if we club these two equations, so we can say F by mg is equals to F by K mg minus FB, where F will get cancelled out. So dielectric constant will be mg upon mg minus FB, and FB is what? So if V is the volume, let's say this is the sphere and the volume is V, then mass will be density of the sphere time its volume, right? Similarly, the buoyant force will be density of the surrounding fluid times the volume submerged times G, right? So let us substitute these values. So mg can be written as sigma Vg divided by sigma Vg minus Fb is rho Vg. So from the numerator and denominator we can eliminate Vg, right? And we will get sigma upon sigma minus rho, and sigma, and you can also remember this formula, right? K equals to sigma upon sigma minus rho. So sigma is 1.5, which is given in the question, 1.5 divided by 1.5 minus 1, right? Dielectric constant of water, okay, if the density, and we have to find the dielectric constant of water, so it comes out to be 1.5 upon 0.5, so it comes out to be 3, right? So the answer will be 3. I hope this solution is clear to you. Now let us see one more illustration. Suppose a uniformly charged wall provides a uniform electric field of 2 into 10 raised to power 4 Newton per Coulomb normally. So we have given a wall, it is uniformly charged, and due to this there will be a field in the right direction, right? So field is in the right direction. A charged particle of mass 2 grams being suspended through a silk thread of length 20 centimeter and remain stayed at a distance 10 centimeter from the wall. So there is a charged particle which is being suspended with the help of a string of length 20 centimeters, sorry. So this length is 20 centimeter and its distance from the wall is given as 10 centimeter. So it means we have given this angle theta, and in this right angle triangle cos theta can be written as base upon hypotenuse, so that will be 1 by 2, so theta comes out to be 60 degrees. Okay. Remain stayed at a distance 10 centimeter from the wall, then the charge on the particle will be, so we have to find the charge on the particle. So again you have to draw free body diagram of the charged particle. So let us draw the free body diagram. So there will be a gravitational force mg, and there will be a force exerted by the uniform electric field, and in case of point charge the force will be q times the electric field, so that will be q times E, and there will be a tension force away from the charge. Now the tension will be opposite to the resultant of mg and qe. So if I draw the resultant of these two forces, if this angle with the horizontal is theta, then this angle is also theta, right? So from this right angle triangle we can say tan theta will be mg by qe. Now what is tan 60 degrees? So tan 60 degrees is root 3, and mass is given as 2 grams, so that will be 2 into 10 raised to power minus 3 and G is given as 10 in the question, and we have to find Q. Electric field is given as 2 into 10 raised to power 4. Let us simplify this. So Q comes out to be 1 by root 3 times 10 raised to power minus 5. That will be minus 6, sorry, 10 raised to power minus 6. And we have given Q is 1 upon root x microcoulomb. So basically, this is microcoulomb, this is micro, and this will be the x. So x comes out to be 3. So 3 is the answer of this question. Right, so now let us see one more question based on the same concept. Two identical charged spheres suspended from the common point by two massless strings of length L and are initially a distance d apart, where d is very small in comparison to L. So let me just draw that. Something like this, right? This distance is d, and d is very small in comparison to length of the string. And right, so the charge begins to leak from both the sphere at a constant rate, and as a result the charge approaches each other with a velocity v. So we have given that the charge is decaying, or it is getting removed from the sphere at a constant rate. So it means dq by dt will be some constant. Let me call this as k1, right? K1 is the constant. As a result of the charges approach each other with the speed v. So v is the speed of approach. So let us say at some later instant, the distance between them is x, and this distance is decreasing at a rate v. So we can say dx by dt is nothing but minus v, right? So dx by dt is the speed of approach, and since x is decreasing, I'm putting a negative sign. So dx by dt will be minus v. Then the velocity, then the function of x between them. So we have to find x as a function, v as a function of x. V as a function of x. Let us do that. So if we draw a free body diagram of the left sphere, let us draw the free body diagram. So there will be a gravitational force mg in the downward direction, and there will be a Coulomb repulsion in the left direction. I'm calling it F, and there will be a tension. And we know that the tension will be opposite to the resultant of F and mg. So if the angle with the vertical is theta, let us say this angle is theta, this is also theta, right? So this is theta, this is theta. So we can say tan theta will be F divided by mg in this right angle triangle. Right, and this theta is decreasing. Okay, and what is tan theta in this case? Since theta is very small, because we have given d is very small in comparison to L, so we can say x is also very small in comparison to L. If x is very small, this angle will be very small. So we can say tan theta will be nearly equals to sine theta. If that is the case, sine theta can be written as, so this perpendicular will be x by 2, and the hypotenuse is L, right? So this can be written as x divided by x by 2 divided by L, so that will be x by 2L. So tan theta is x by 2L. Force can be written as k q square divided by r square. R will be x square times mg, right? So here, can you see, we have x as a function of q. So we can say x cube will be directly proportional to q square. And if we differentiate this equation, this proportionality, so we will get 3x square times dx by dt will be proportional to 2 times q dq by dt. And we have given dq by dt is constant and dx by dt is the velocity. So if we further simplify this, here we have q and here we have x square. So we can say dx by dt. So this can be written as v. So v will be proportional to q divided by x square. Now if you look at this proportionality, we can write q as a function of x. So q can be written as x raised to power 3 by 2, and we have x square in the denominator, so we can say v will be proportional to x raised to power 3 by 2 minus 2, and that will be x raised to power minus 1 by 2. So if you look at the option A is the right answer. I hope this question is clear to you. Now let us see the next problem type, tension in a circular ring. So a thin metallic wire having cross-sectional area 10 raised to power minus 4 square meter is used to make a ring of radius 30 centimeter. So basically we have given a ring and the radius is given as 30 centimeter. So that is 30 centimeter. And the area of cross section of the wire with which we are making the ring, that area of cross section is given as 10 raised to power minus 4 square meter. A positive charge of 2 pi coulomb is uniformly distributed over the ring. So on this ring there will be a positive charge which is distributed uniformly. So the total charge on the ring is 2 pi coulomb. While another positive charge of 30 picocoulomb is kept at the center of the ring. Now there is a charge of 30 picocoulomb at the center. Now the tension in the ring is, so basically we have to find the tension in the ring. Provided the ring does not get deformed, neglect the influence of gravity. So, and we have given 1 upon 4 pi epsilon naught is 9 into 10 raised to power 9 in SI units. So actually what is happening in this case, because of this 30 picocoulomb charge, each element of the ring will experience a repulsive force, and that force will be in the radially outward direction. So if you consider this particular element, it will experience a repulsive force in the radially outward direction. Right, so let us, so there is a technique to solve such kind of question where you have to find the tension. So let us take a small element. So I'm going to consider a small ring element which is located, which subtends an angle, say d theta, or let us take it as theta only, theta where theta is very small. So this angle is theta, and this arc length, we can say it will be r dr theta, right? So that will be r theta, and it's a uniform wire, right? So what is the charge on this small element? So we can say dq is the charge on this small element, dq. So dq can be written as total charge, that will be 2 pi coulomb, divided by the circumference charge per unit length times the length of the element. So it will be 2 pi r, and r is given as 30 centimeters. So let me write it as 0.3 meters multiplied with the length of the element, which is r theta, and r is 0.3 and theta. So that is the charge. So this 2 pi will get cancelled out, 0.3 will cancel out with 0.3. So we are getting theta, right? So dq is nothing but theta numerically. So what is the force experienced by this element? So there will be a Coulomb repulsion. So if I show the free body diagram of this element, so there will be a tension force which is along the wire. So this is T and this is T, and this angle is theta. So if we try to see all the forces acting on this element, so there will be a repulsive force which will be in the radially outward direction, and that is nothing but K dq, which is theta, times the charge at the center, which is 30 picocoulomb, divided by 0.3 square, right? So that is the force. Now let us resolve tension in vertical and horizontal direction. So this component, so this angle will be theta by 2. So this component will be t sine theta by 2, right? Similarly, here we'll get the same component t sine theta by 2. Now, the horizontal component will get cancelled out. T cos theta by 2 will cancel out with t cos theta by 2. So we can say if this element is in equilibrium, then 2 times t sine theta by 2 should balance the Coulomb repulsion on this element. So we can say K theta times 30 pico, that is 10 raised to power minus 12, divided by 0.3 square should be equals to 2t sine theta by 2. Since theta is very small, sine theta by 2 can be written as theta by 2. So if you look at this equation, we can remove theta, and k is nothing but 9 into 10 raised to power 9 and 2 will get cancelled out with 2. So from here we can say the tension will be 9 into 10 raised to power 9 times 3 into 10 raised to power minus 11 divided by 9 into 10 raised to power minus 2. So 9 will get cancelled out, and if you look at this, it will be nothing but 3. So the force experienced, so the tension in the ring will be 3 Newton. So that is the approach whenever you have to find the tension in a circular ring. Right, so now let's see the another problem type, electric field calculation. An infinite plane sheet of charge having uniform surface charge density sigma s is placed on xy plane, and another infinite long sheet line charge having uniform linear charge density lambda e coulomb per meter is placed at z equals to 4. Okay, let me first draw the diagram. So we have given a sheet, infinite sheet, which lies in the xy plane. So let us take this as x and this as y, and it has a positive charge. Now due to this positive charge, there will be electric field everywhere. Okay, and there is a infinite long line charge having linear charge density as lambda e coulomb per meter is placed at z equals to 4. So if this is the z-axis, so somewhere here this is z equals to, it will be 0, 0, 4 meters and parallel to the y-axis. So there is an infinite line charge which is parallel to the y-axis. Again, it's a positive charge. If the magnitude values of sigma s is equals to 2 times lambda e, then at point 0, 0, 2, so basically we have to find at this particular point, which is 0, 0, 2, the ratio of the magnitude of the electric field due to the sheet or to the line charge. Okay, so let us say E C is the electric field. Okay, let me take another nomenclature. Let us say E1 is the electric field by the infinite sheet, and that is given as sigma upon 2 epsilon naught, right? So that is the formula of electric field by an infinite sheet, and sigma is given as sigma s upon 2 epsilon naught, and E2 is the electric field by the line charge, and for the line charge it is given as lambda upon 2 pi epsilon naught times r, where r is the perpendicular distance from the line charge. So lambda is given as lambda e upon 2 pi epsilon naught, and r in this case will be what? So the distance of the point where we want to find the field is 2 meters from the line charge, so that will be 2. And we have to find the ratio of the electric field. So E1 by E2 will be given as sigma s upon 2 epsilon naught times 4 pi epsilon naught time upon lambda e. So let us cancel the common factors. So it comes out to be sigma s by lambda e is nothing but 2 times 2 pi. So it comes out to be 4 pi. And we have given it is pi times root n upon 1. So that is given as pi times root n upon 1. So we can say root n is equals to 4. So n will be 16 if we square on both sides. Right, so the answer will be 16. Right, so let us see the next question. Two charges q and 3q are separated by a distance r in the air. At a distance x from the charge q, the resultant electric field is 0. The value of x. Okay, so we have given two charges q and 3q, and the distance between them is r. And they're placed in air. At a distance x from charge q, the resultant electric field is 0. Okay, so if you want to find the position of the point where the field is 0, since we have like charges, it has to be somewhere in between the two charges. Is it clear? It has to be somewhere in between two charges, because if you consider a point to the left of q, the electric field direction by both the charges will be towards left, so it can't be 0. And if you consider a point towards the right of 3q, both the field will be in the right direction, because for the positive charge the field is always away from the positive charge. So here it can't be possible. On to the left of q it is not possible. So there has to be some points in between the two charges. So let us take it as, so let us say this is the point P where the field is 0, and this distance is given as x. So this will be r minus x. So at P we can say there will be a field by 3q in the left direction, and that will be k 3q divided by r minus x square. So that is the formula of electric field by a point charge. And due to the charge q, there will be a field in the right direction, and that will be kq by x square. Since the field at P is 0, these two values should be equal. So kq will get cancelled out. Let us take the square root on both sides. So that will be root 3 upon r minus x equals to 1 by x. Now from this, root 3 x equals to r minus x, and x will be r upon root 3 plus 1. Right? So if you look at the options, option 3 is the right answer. Right, so let us see another question. Sigma is the uniform surface charge density of a thin spherical shell of radius r. So we have given a thin shell which is having a radius r. It has a uniform surface charge density sigma. The electric field at any point on the surface of the spherical shell. So electric field at the surface is defined as kq upon capital R square, where q is the total charge on the shell. On the surface or outside the surface, if you want to find the field, you can treat shell just like a point charge concentrated at the center of the shell. So what is q? So total charge will be surface charge density times the surface area of the shell, and surface area is 4 pi capital R square. Let us substitute the value. K is 1 upon 4 pi epsilon naught. Q is sigma times 4 pi r square divided by r square. So r square will get cancelled out, 4 pi will get cancelled out. So it comes out to be sigma by epsilon naught. So option 2 is the right answer. Let us see another illustration. 3 infinite long charged thin sheets are placed as shown in the figure. The magnitude of the electric field at the point P is x sigma by epsilon naught. The value of x is. So we have to find the field at point P which lies between these two sheets. So there are overall 3 sheets. So basically we have to find the field by all the 3 sheets at the location P, and then we have to vectorally add the field. Now due to this sheet 1, it is having negative charge, so the field will be in the left direction, so that will be even. And due to the second sheet, let me take it as blue, due to the second one, the field is again negative, so it will be in the left direction, that will be E2. And due to the third sheet, it is given as sigma, take it as 3, so it will be away. So in case of a negative, it will be towards the negative charge. In case of a positive charge, it is away from the positive charge. So we can say E3 is also in the left direction. So all the 3 fields are in the same direction. So we can say the net field Field at P will be E1 plus E2 plus E3. And what is the formula of electric field by a sheet of charge? It is sigma by 2 epsilon naught, right? So that is the formula of electric field by a infinite sheet of charge. So E1 will be sigma by 2 epsilon naught, and E2 will be 2 sigma by 2 epsilon naught, and E3 will be sigma by 2 epsilon naught. So it comes out to be 4 sigma by 2 epsilon naught. So it will be 2 sigma by epsilon naught. So the answer will be 2, right? Got it? Let us see next question. If the net electric field at the point P along the y-axis is 0, so at P the field is 0, then the ratio of the magnitude of Q2 and Q3 is 8 upon 5 root x. What is the value of x? Right, so at P, if I show the force due to this positive charge, the field will be away from the positive charge, right? Let me call this as E1. This is charge E2. Let us take it as E2. So this is charge number 2. Let us this charge number 3. And due to this charge number 3, the field will be towards the negative charge. So that will be E3. Now the first step would be we have to find the magnitude of E2 and E3. So let us find that. So what is the distance of Q2 from point B? So let us take this distance as, so it will be the hypotenuse of this right angle triangle. So it will be 2 square plus 4 square. So that comes out to be 4 plus 16. So that will be root 20, right? Similarly, if I want to find the perpendicular distance of P, so distance of P from minus Q3, it will be root of 4 square plus 3 square, which is nothing but 5. So first let us find E2. It will be K Q2 divided by root 20 square, where root 20 is in centimeters. And E3 will be K Q3 divided by 25. Again 25, here 5 is in centimeters. And we have given that the net field at point P along the y-axis. So what do we mean by that? So it means the net electric field at point P along y-axis is 0. So field in the y direction is 0. It means the component of EY and E3 in the vertical direction, they are cancelling each other out. So let us find the component. This is E2. This is E3. Let us say this angle is theta 3 and this angle is theta 2. So this will be theta 2 and this will be theta 3. So what is the vertical component of E2? So that will be E2 cos theta 2, and vertical component of E3 will be E3 cos theta 3. So E2 cos theta 2 should be equals to E3 cos theta 3. So it will be K Q2 by 20 times cos theta 2 should be equals to K Q3 by 25 cos theta 3. Now what is cos theta 2? So cos theta 2 will be base upon hypotenuse. So that will be 4 by root 20. And cos theta 3 will be again base upon hypotenuse, which is be 4 by 5. Now let us put the values. So this k will get cancelled out. This will be 4. This will be 5. So we can say Q2 by Q3 will be 4 by 5 times cos theta 3, which is 4 by 5, divided by cos theta 2, which is 4 by root 20. So let us simplify this. This 4 will get cancelled out and we get 4 upon 5 square times root 20. And root 20 can be written as 5 times 4. So it will be 4 by 25 times 2 root 5 So that will be 8 upon 25 root 5, right? So we can say 8 upon 25 root 5 is equals to 8 upon 5 root x. So that is given. So 8 will get cancelled out. It will give us 5. Now if you take the square on both sides, it comes out to be 5 upon 25 equals to 1 by x. And from this, x comes out to be 5. Right? So the answer will be 5. Right, so now let us see the next problem type, and it is based on equipotential surface. So here you should know the properties of equipotential surface. So let us see the question, and question usually based on questions will be qualitative in nature from this particular type. So given below are two statements. One is labeled as assertion, other is reason. Assertion is given: work done by the electric field on a moving point charge, positive charge on an equipotential surface is always 0. So it is saying if we have a say some equipotential surface and we are moving a charged particle on this equipotential surface, positive charge, then the work done is 0, and the reason is electric lines of force are always perpendicular to equipotential surface. So that is the property. So electric field lines are always perpendicular to equipotential surface. So if the electric field lines are perpendicular, and so these electric field cannot do any work on the charged particle because there is no component of electric field which is parallel to the surface. So we can say reason is the right explanation for the assertion. So option 4 should be the right answer. Both A and R are correct, and R is the correct explanation of A. Right, so let us see the next problem type. It is based on motion of charged particle in uniform electric field. So when a charged particle is moving in electric field, it will experience a force which is given by Q times E. For a positive charge, it is along the electric field. For a negative charge, it is opposite to electric field. So let us see some illustration. An electron is moving under the influence of electric field of a uniformly charged infinite plane sheet S having a surface charge density plus sigma. So we have given an infinitely long sheet of charge which is having uniform surface charge density plus sigma, and due to this positive sheet the field will be normal to the sheet at every point, and the field will be uniform. So the electron at t equals to 0 is at a distance 1 meter from S. So we have given there is an electron which is at a distance of 1 meter from the sheet and has a speed of 1 meters per second. Okay, so that is not mentioned here, but this speed is away from the sheet. So the speed is in the right direction, that is 1 meters per second. And if I show the force, the electron will experience an attractive force that will be in the left direction, and due to this attractive force there will be an acceleration in the left direction. So the maximum value of sigma if the electron strikes S at 1 second is alpha times m epsilon naught by E, the value of alpha. So we have to find the value of alpha. And if I show the trajectory of the electron, first it will slow down because the force is in the left direction, velocity is in the right direction, and at certain instant its velocity will become 0 for a moment, and then it will retrace its path, and then it will hit the plate at t equals to 1 second. So if you want to find the value of sigma, we can apply kinematics. So we have given this, if I consider left direction is positive, acceleration is given which is charge times the electric field. Electric field by the infinite sheet of charge will be sigma by 2 epsilon naught divided by mass. So that is the acceleration produced in the electron. Displacement is in the left direction which is 1 meter, and initial velocity is in the right direction, that will be 1 minus 1 meters per second, and time is 1 second. So we can apply S equals to ut plus half at square. So S is 1, u is minus 1, t is 1 plus half. Acceleration is a sigma upon 2 m epsilon naught times 1 square. So from this, sigma comes out to be 8 m epsilon naught by E. So if you compare this result which is given in the question alpha comes out to be 8. So 8 is the answer of this question. Let us see another type. Another problem based on the motion of charged particle in electric field. A point charge minus q and mass m moves in a circle of radius r. So we have given a point charge which is moving in a circular path of radius r and around an infinitely long charge of linear charge density lambda. So we have given an infinitely long line charge which is having linear charge density lambda. So and the electron is moving in a circle. So there is an electron which is moving in a circular path around this line charge, and the center of this circular path will lie on the line charge. So if I show the negatively charged particle minus q, which is having a mass m, so it will feel an attractive force which is toward the center of the circle, and this Fe will be given as the charge times the electric field by the infinite line charge. Now what is the formula of electric field by line charge? It is lambda upon 2 pi epsilon naught times r. So it will be q lambda 2 pi epsilon naught times the radius of the circular path. And since it is moving in a circular path with constant speed, it should be equals to the centripetal force, which is given as mv square by r. Now from this equation we can find the speed of the charged particle. So v square comes out to be q lambda upon 2 pi m epsilon naught, and so v comes out to be root of q lambda upon 2 pi m epsilon naught. So we got the velocity. So if we want to find the time of one orbital time period, so that will be circumference by the velocity, right, by the speed. So times 2 pi m epsilon naught by q lambda, and the option we have given k. So k is 1 upon 4 pi epsilon naught. So we can say 1 upon pi epsilon naught is equals to 4k. So from here this can be written as 2 pi r root m upon 2k lambda q. So option 2 is the right answer. Let us see another illustration. A uniform electric field E, which is 8 m by E volt per meter, is created between the two parallel plates of length 1 meter as shown in the figure. M is the mass of the electron, E is the charge, and electron enters the field symmetrically between the plates with a speed of 2 meters per second. So it is coming with a speed of 2 meters per second, which is parallel to the plates. The angle of deviation of the path of the electron as it comes out of the field. Now in this case, as the electron enters, electric field is in the downward direction from positive to negative plate. It will experience a force opposite to the electric field because it's a negatively charged particle. So that is the force. Due to this force, and velocity is in the horizontal direction, force is in the vertical direction, it will be having a parabolic trajectory. Okay, it will follow a parabolic path, and then it will have a horizontal displacement of 1 meter, and it will come out of the plates. So it will come out of the influence of electric field. So at this particular point, it will be having a velocity which is making an angle theta with the horizontal. So it will be having two components, Vy vertical component and the horizontal component Vx. So I'm taking right direction as positive x, upward direction is positive y. So we have to find theta, and tan theta can be given as Vy by Vx. So let us find Vy and Vx. Since there is no acceleration in the horizontal direction, Vx is nothing but the ux, that is the velocity just before entering the plates. So it is nothing but 2 meters per second. So in order to find Vy, we can use Vy equals to uy plus ayt. So for that we need to find what is the time taken by the charged particle from position 1 to position 2. So in the horizontal direction, the displacement is 1 meter. Velocity in the horizontal direction is 2 meters per second. So we can find the time, that will be displacement upon speed. So that will be nothing but 1 by 2 seconds. So we got the time. Now we can substitute this time in this equation. velocity in y direction we have to calculate. Uy is 0 because the electron is moving horizontally initially, so that is 0. And what is the acceleration? Acceleration will be E times capital E by m, and E capital E is given as 8m, right? So acceleration comes out to be 8 meters per second. So this will be 8, and time is 1 by 2, so it comes out to be 4 meters per second. Now we can substitute value of Vx and Vy in this equation. So Vy is 4, Vx is 2, so it comes out to be 2. So theta comes out to be 10 inverse 2. So option B is the right answer. Right, so now let us see the next type of problem type where we have to find the electric flux. So first let us see a case when the electric field is uniform. So here we have given electric field as 2 I cap plus 6 j cap plus 8 k cap. So it's a uniform field, right? Passes through a surface of area 4 square meter, and the area vector is in the direction 2 I cap plus j cap plus k cap by root 6. So basically it is the unit vector, right? So if I want to write down the area vector, it will be magnitude times the unit vector. K cap divided by root 6. And in case of a uniform electric field, the electric flux is given as E dot A. So let us take the dot product. So if we take the dot product, we have to multiply the components in the x direction, y direction, and z direction, and then we have to add them. So we can say it will be 1 by root 6 times 4 by root 6 times 2 times 2 plus 6 times 1 plus 8 times 1. So this comes out to be 2 by 3, 4 plus 6 plus 8. So 18 times 2 by 3, so that will be 12 volt meter. So the flux through this area will be 12 volt meter. Now let us see the illustration where electric field is variable. So here electric field is given as 2x I cap. So it is varying with x. Exists in space, and the direction is also fixed. It is in the right direction, in the x direction. A cube of side 2 meter is placed in the space as per the figure given below. The electric flux through the cube is, so here we have given a closed figure, that is a cube. So in such cases you have to find flux through each face, and then you have to algebraically add them. So so electric field is in the right direction. And if you look at the lateral surfaces, like the top surface, the area vector outward. So in case of a closed figure, we should take outward normal as the area vector. So this area vector for the top face will be in the upward direction, and the electric field is in the horizontal direction. So there will be no flux linked with the top surface. Similarly, for the bottom surface, the electric field is in the right direction, but the area vector is in the downward direction, which is in the negative y. Again, there will be no flux linked with the bottom surface because it's the dot product will become 0. And for the front surface, the area vector will be in the z direction, and electric field is in the x direction. Again, there will be no flux. Similarly, we can say there will be no flux with through the back surface, where area vector will be in the negative z direction, and electric field is in the right direction. So we are left with left face and the right face. And for the left face, the outward normal is in the left direction, and its value, it's a cube of side 2, so that will be 4 square meter. But electric field is in the right direction, and if you look at the value of x at the left face, the value of x is 2 meters, so electric field will be 4 Newton per coulomb in the x direction. So the flux linked with the left face will be, the angle between area vector and the electric field is 180 degrees, so it will be negative of 4 times 4, that will be minus 16 Newton meter square per coulomb. Similarly, if we want to find the flux linked with the right face, the area vector will be in the outward normal direction, that will be in the positive x direction. This will be 4 square meter, and electric field is also in the same direction. But the value of x has changed. For the right face, the value of x will be 2 plus 2, 4. So 4 times 2 will be 8. So this will be 8 Newton per coulomb. So flux linked with the right phase will be 4 times 8, that will be 32 Newton meter square per coulomb. So now we have to just add the individual flux. So it comes out to be 32 minus 16. So it will be 16 Newton meter square per coulomb. So so the answer will be 16, right? So let us see the another problem type which is based on the application of Gauss's law. So we have given two charges 5q and minus 2q are situated at a point 3a comma 0 and minus 5a comma 0. The electric flux through the sphere of radius 4a having center at origin is. Okay, let me first draw the diagram. So we have given, so this is the x-axis, and let us say this is the y-axis, and there is a charge 5q which is placed at 3a comma 0, and there is a charge minus 2q which is placed at minus 5a comma 0. So if I consider a Gaussian surface which is given in the question, the Gaussian surface is having a radius 4a and having a center at the origin. So let's say this is the Gaussian surface. For this Gaussian surface, by Gauss's law, the flux through the closed surface will be given as Q enclosed by epsilon naught. So how much charge is being enclosed by this Gaussian surface? It will be nothing but 5q, because minus 2q is outside. So it will be 5q by epsilon naught. So this is the answer, option 2. Let us see another question. So we have given C1 and C2 are two hollow concentric cubes enclosing charge 2q and 3q respectively as shown in the figure. So if you look at the figure, the small cube is having 2q charge enclosed, and 3q lies between the outer cube and the inner cube. So if I show this in 2 dimension, uh, right, so let me draw that. So so there is a 2q charge here, and there will be 3q charge in this region, right? So in this region the charge will be 3q. So we have to find the ratio of the electric flux through C1 and C2. So for C1, Q enclosed is 2q, and for C2, Q enclosed is 2q plus 3q. So if you want to find the ratio of the flux, so ratio of the flux is proportional to the charge enclosed. So 5c1 upon 5c2 will be 2q by 5q, right? So that will be 2 by 5. So option 1 is the right answer. So let us see another illustration. A charge q is placed at the center of one of the surface of a cube, the flux linked with the cube. So we have given say a surface yeah. Okay, so suppose this is one of the face of the cube, and we and the charged particle is placed at the center of this surface, right? So if we complete the other, if I show other faces of this cube, something like this, right? So we have to find the flux linked with the cube. So so we can say there will be no flux linked with the face which contains the charge, right? So how to do that? So in this illustration we have given a charge q which is placed at the center of one of the surface of the cube. Right, so let me draw the cube. So the charge is placed, let us say, at the left, at the center of the left face. And we need to find the flux linked with this cube. So in such questions, what do we have to do? Let us consider one more cube such that the charge will be at the center of the figure, right? So if I consider one more cube at the left, and if we apply symmetry, so we can say by symmetry the flux linked with this purple cube will be same as the flux linked with the black one. And if we consider this entire region, this cuboid as a Gaussian surface, so cuboid as Gaussian surface, then we can say the total flux will be the q by epsilon naught. So if the flux is linked equally on these two cubes, we can say the flux linked with the cube will be q by 2 epsilon naught. So option 1 is the right answer. Next, we are given 5 charges plus q plus 5q minus 2q plus 3q minus 4q are situated as shown in the figure. The electric flux due to this configuration through the surface S. So in such question, you have to find the charge enclosed by the Gaussian surface. So here, so we have given, yes, so here we have 5q, q and 2q. So let us find. So this will be plus 5 and this will be plus 3q and this is minus 4q and this is plus q and this is minus 2q, right? So this is plus q, right? So what is the charge enclosed? So q enclosed will be plus 5 plus 1 minus 2q. So that will be 4q. So the flux by Gauss's law will be 4q by epsilon naught. So option 1 is the right answer. Right, so let us another illustration, and we have given a statement 1. An electric dipole is placed at the center of a hollow sphere. The flux of electric field through the sphere is 0, but the electric field is not 0 anywhere on the sphere. So it is saying, so we have given a sphere, and at the center of the sphere we have placed a dipole. So this will be plus q, this will be minus q. So it is saying that the electric field is not 0 anywhere on the sphere, but the flux will be 0. Yes, the flux is 0 because q enclosed is 0. But electric field will be having a non-zero value, right? For example, if this is the direction of electric dipole moment, so at this particular point the electric will be in the left, in the right direction. Here it is in the right direction. So at this particular point it is in the left direction, right? At this particular point it is in the left direction. So electric field will be having a non-zero value on the sphere, but the flux will be 0. Statement 1 is fine, that is correct. Now statement 2, if r is the radius of the solid metallic sphere and q be the total charge on it, the electric field at any point on the spherical surface of radius r is 0, but the electric flux through this closed spherical surface of radius r is not 0. Okay, right, so let us see. So it is saying, if we have given a solid metallic sphere of radius r, and on this sphere the charge is q, the electric field at any point on the sphere for r less than capital R. So if we consider a point, say P, where the distance from the center is small r, which is less than capital R, the electric field, but the electric flux passing through this closed spherical surface of the radius r is not zero. That is incorrect. So flux in this case is also zero because the charge on a spherical shell is always resides on the outer surface. So there will be no flux linked with this sphere, right? So statement 2 is incorrect, whereas statement 1 is fine. So that is, so statement 1 is true, but the statement 2 is false. So option 2 is the right answer. Right. Right. So now let us see the next problem type, which is where we need to find the electric potential. Right. So let us see a question based on that. An electric charge which is 10 raised to power minus 6 microcoulomb is placed at the origin, which is 0, 0 in the xy plane, and 2 points P and Q are situated at root 3, root 3 and root 6, 0. The potential difference between the point P and Q will be. Right. So let me first draw the diagram. This is the x-axis and this is the y-axis, and we have given 2 points P and Q. So this point is root 3, root 3, and Q point is root 6, 0. That is Q. The potential difference between point P and Q will be, so we have given a charge of 10 raised to power minus 6 microcoulomb is placed at the center. So the potential difference. So in order to find the potential due to a point charge, we can use this formula kq by r. So for that we need to find the distance of charge from point P. So by distance formula, this distance will be root of 3 plus 3, that will be root 6. Similarly, this distance is also root 6. So point P and Q are equidistant from the charge. So we can see the potential at P will be equals to the potential at Q. So Vp minus Vq will be 0. So option 3 is the right answer. Right, now let us see another illustration. The electric potential at the surface of an atomic nucleus of atomic number 50 of radius 9 into 10 raised to minus 13 centimeter is. So we have to find the electric potential. So what is the total charge? So that will be Z times E, and electric potential will be KQ by R, and this will be 9 into 10 raised to power 9, and the charge will be 50 times 1.6 into 10 raised to power minus 19 divided by R, and R will be 9 into 10 raised to power minus 13 centimeters, so 10 raised to power minus 2. So now we have everything in SI units, so this 9 will get cancelled out. So 16 times 5 is 8, so this will be 80. 80 times 10 raised to power 9 minus 19 plus 13 plus 2. So this comes out to be 80, and we have 24. So this will be 9 plus 13, 20, 22, 24 side. So 10 raised to power 5. So it comes out to be 8 into 10 raised to power 6 volts. So if you look at the, so we have to fill the blank where the value will be 8. So 8 is the answer. So in this illustration, at the center of a half ring of radius 10 centimeter and linear density, charge density 4 n coulomb per meter, the potential is x by volts. The value of x is, so here we have given a semicircular ring which is having a charge. Linear charge density is given, so lambda is given as 4 nano coulomb per meter, and we need to find the potential at the center, and the radius is given as 10 centimeters, so 0.1 meter. So in case all the points on this semicircular ring are equidistant from the point where we need to find the potential, so potential at O will be what? It will be K times the total charge on the ring divided by the radius of the ring. So it will be 9 into 10 raised to power 9 times q will be so lambda is given, so q it will be lambda times the length. So lambda 4n and the length will be pi r. So pi times 0.1 divided by the radius. Radius is given as 0.1. So this comes out to be 36 into 10 raised to power 9, and this is nano. So minus 9 minus 1. So this comes out to be 36 times zero point 0.1 by zero point 0.1. So it will be 36, and pi is also there, right? So 36 pi. So if we compare, x comes out to be 36. So 36 is the answer of this question. Right. So let us say this illustration, it is again based on the same concept. The electric potential at the center of two concentric half rings of radius r1 and r2 having same linear charge density lambda is. So we know that in case of a ring, the potential at the center will be total charge k times total charge by the radius of that ring. So we can say it will be for outer one, it will, contribution towards the potential will be k lambda times r2 times pi divided by r2, and for the contribution towards potential by the inner ring will be k times total charge, it will be lambda times pi r1 divided by r1. So r1 will cancel out with r1, r2 with r2, so we left with 2k lambda pi, or we can write this as lambda pi times 2 divided by 4 pi epsilon naught. So pi will get cancelled out, it will give us 2 here, so lambda by 2 epsilon naught. So option 2 is the right answer. Now let us see another problem type where we have to connect conductors. So two charged conducting spheres of radius a and b are connected to each other by conducting wire. The ratio of the charge of the two spheres respectively. So when we have two conductors which is having a radius a, this is having a radius b, and now we are connecting them with a conducting path. So the charge will flow from positive charge will flow from high potential to low potential, and the charge will ceases to move when both the sphere attain same potential. And in this situation, the final charges will be proportional to the radius. So do remember this. So if this is Q1 and this is Q2 final charges, so Q1 by Q2 will be A by B. And if you want to find the surface charge density, so surface charge density will be inversely proportional to the radius, so B by A. So option 1 is the right answer of this question. Next, so two isolated metallic solid sphere of radius r and 2r are charged such that both have same charge density sigma. The spheres are then connected by a thin conducting wire. If the new charge density of the bigger sphere is sigma prime, then what is sigma prime by sigma? Right, so sigma is the original surface charge density. So they have same. So if I give, so we have given a small sphere and a big sphere, right? So this sphere has a radius r, this sphere has a radius 2r, and they have same surface charge density sigma. Now the spheres are then connected. So when we connect these two spheres, so what is the so first let us find the initial charge. So Q1, let me call this as sphere 1 and this is sphere 2. So Q1 will be sigma times 4 pi r square, and Q2 will be sigma times 4 pi 2r square. So now this total charge will get distributed on both the spheres. So the new surface charge density of bigger sphere is sigma prime. So we know that sigma prime, or let me call this as sigma 2 by sigma 1 will be r by 2r, right? because surface charge density is inversely proportional to the radius. And the final charge on the sphere, so if I call this final charge on the second sphere as q2 and final charge on the first sphere as q1, so we can say q2 by q1 will be 2r by r, so that will be 2. And what is the total charge? So by charge conservation, q1 plus q2 should be equals to small q1 plus small q2, so it will be so this is 4, so it will become 4 times sigma 4 pi r square, so it will become 5 times sigma 4 pi r square. So that is the total charge. Now from these two equations we can find the final charge on the big sphere. So q2 will be 2/3 of total charge, that will be 20 sigma pi r square. Now we want to find the surface charge density on the big sphere, so sigma prime will be q2 divided by the surface area 4 pi r square, that will be 4 r square, and this q2 will be 2/3 times 20 sigma pi r square. So let us simplify this. So r square will get cancelled out, pi will get cancelled out, so it will be 4 and this will be 5, this will give us 2, so it comes out to be 5 divided by 6 sigma. So sigma prime is 5 by 6 sigma, so 5 by 6 should be the answer, right? Option 4 is the right answer. Right, so next type of problem type is when we coalescing the two drops or more than two drops into a giant drop. So let us see a question based on that. 64 identical drops, each charged up to the potential 10 millivolt, are combined to form a big drop. So we have given 64 small drops. Let us say the radius of this small drop is small r and the charge is small q. And each is being charged to 10 millivolts. So what is the potential of the single drop? It will be k q by r, and that is given as 10 millivolts, right? Now what we have done, we have joined the 64 drops into a single drop. So in such questions you have to conserve volume. So we can say volume of 64 drops should be equals to volume of big drop, right? And let's say the big drop has a radius capital R. So 4 by 3 pi small r cube times 64, that should be equals to 4 by 3 pi capital R cube. So if so this 4 by 3 pi will get cancelled out. Let us take cube root on both sides, so that will become 4r equals to capital R. So we have the relation what is capital R in terms of small r. Now we have to find the potential of the big drop. So potential of big will be, so by the charge conservation, the charge on big drop will be 64 times the charge on one drop. So we can say k 64 times q divided by r, and r is 4 times small r, right? So this can be written as 64 by 4 times kq by r, and kq by r is 10 millivolts. So this will be 160 millivolts, right? So 160 is the answer of this question. And this question is based on the same concept that you can do on your own. The same logic we have to apply. Right, so now let us see the next type of problem type, and we have concentric shells. So three concentric spherical metallic shells X, Y, and Z of radius A, B, and C, and we have given C is greater than B and B is greater than A, have surface charge density sigma minus sigma and plus sigma. Okay, so let me first draw the diagram. So that is given. So three concentric shells and the radius. So this radius is given as A, this is B, and this radius is C. And if you talk about the surface charge density, inner sphere has a surface charge density sigma, middle one is having minus sigma, and outer one will be having sigma. The shell X and Z are at same potential. So the potential of shell innermost shell and the outermost shell are at the same potential, 1 and 3. So we can say V1 is equals to V3. If the radii of X and Y are 2 and 3 centimeter respectively, the radius of shell Z. So basically we have to compare the radius, right? Okay, right. So let us do that. So potential of 1 and 3 is equal. So let us find the potential of 1. So the contribution towards potential by at 1 will be due to the charges of all the three shells. So we can say V1 will be charge on the inner shell will be sigma times 4 pi a square times k divided by a, and the contributions towards potential on the inner shell will be by the middle shell will be minus sigma 4 pi b square k divided by the radius of the middle shell, that will be b, plus now the contribution due to the charge on the outermost shell, that will be sigma times 4 pi c square times k divided by c. So if we simplify this, so it comes out to be 4 pi sigma k will be common. So a minus b plus c. Got it? So that is the potential of the innermost shell. Now what is the potential of the outermost shell? So potential of the outermost shell will be again the contribution by all the charges present. So due to the charge on the inner sphere, it will be k 4 pi a square times sigma divided by c, and due to the inner charge on the inner shell, it will be k 4 pi b square times sigma divided by c, and due to the outermost, it will be k sigma 4 pi c square divided by c. So if we simplify this, 4 pi sigma k by c will be common, and we have a square minus b square plus c square. Now these two values, so v1 is equals to v3. So let us equate them. So v1 is 4 pi sigma k a minus b plus c, that should be equals to 4 pi sigma k by c, a square minus b square plus c square. So let us simplify this. So 4 pi k sigma will get cancelled out. So we have ac minus bc plus c square equals to a square minus b square plus c square. So c square will get cancelled out. And we have to find c. We have to find the radius of the outermost shell c. So c we have to calculate. So c will be a square minus b square by a minus b, which is a plus b. So a is given as 2 centimeter, so b is given as 3, so the answer will be 5 centimeter. So that is the answer of this question. Right, so now let us see the next problem type. So it is about electric potential by a dipole. So if you remember, in case of a dipole, short dipole, I'm talking about short dipole, if P is the electric dipole moment, and then if you want to find the potential at a general point, let us say we want to find the potential at A, where this angle is theta and this is r vector, then potential at A is defined as Kp dot r cap divided by r cube. Oh, sorry, not r cube, r square. This will be r square, or we can also write this as Kp dot r upon r cube. And if theta is 0, then the position is known as the axial position, and in axial position the potential will become kb by r square. And if theta is 90 degrees, then potential will become 0, right? Potential will become 0. So let us see the question. So electrostatic potential due to an electric dipole at a distance r varies as. So we know that potential is given as k p dot r cap divided by r square, or we can write this as kp cos theta divided by r square. So we can say potential is inversely proportional to square of the distance from the dipole. So option 2 is the right answer. Let us see another illustration. The distance between the charge q plus q and minus q is 2L. So this distance is given as 2L, and between sorry, this is 4L basically. This is 4, and the distance between small q's is 2L. Right, the electrostatic potential at a point P at a distance r from the center. So here I'm assuming short dipole. Okay, so what we can say, plus 2q and minus 2q, they'll form one of the dipole, right? And for this, let me call that the dipole moment is P2, and it will be 2q times the distance between the two charges, which is 4L. So it comes out to be 8QL. And for plus q and minus q, for this the dipole moment will be q times 2L. Now what is the direction? In this case it will be from left to right, so that is P1 vector. And for plus 2q and minus q, the electric dipole moment is in the left direction, from negative to positive charge, so that will be P2. Now what is the angle between P2 and the r vector? So angle between P2 and r vector will be this angle, right, which is 180 minus 60, that is 120 degrees. An angle between P1 and r vector will be 60 degrees. Okay, so potential at P will be potential due to the first dipole plus potential due to the second dipole. So we can write this as, for first it will be k P1 cos 60 degrees divided by r square, and due to the second one it will be k P2 cos 120 degrees divided by r square. Now let us substitute the values. So k by r square will be common. P1 is 2QL, and cos 60 is 1 by 2, plus P2 is 8QL, and cos 120 is minus 1 by cos 120 will be minus 1 by 2. So it will be yeah, so kp by r square is outside. So this comes out to be QL, and this will be 4QL. So this will be QL minus 4QL times k by r square. So it will be minus 3QL k by r square. So minus 3, and we have to find the potential at point P. Okay, let us put the values. So it will be minus 3 into 9 into 10 raised to power 9 QL by r square. And here we have given this is equals to minus alpha QL by R square into 10 raised power 9. So if we compare left hand side with the right hand side, 3 into 9 is 27, and that will be equals to alpha. So alpha will be 27. So I hope this question is clear to you. Right, so now let us see the next problem type. It is the electric field by a dipole. Okay, so usually there are two important positions. So let me just give you the idea. If this is short dipole, then at a general point, say at a point A, if this is the r vector of point A from the center of the dipole and this angle is theta, then the electric field at A is defined as Kp by r cube root of 3 cos square theta plus 1, right? So if theta is 0, then electric field will become 2 Kp by r cube. If theta is 90 degrees, then electric field will become Kp by r cube. So this is the case of axial position, this is the case of equatorial position, and in equatorial position the electric field will be, the direction of the electric field is opposite to the direction of electric dipole moment. Right, so if we want to find the general angle, so the angle made by the net electric field at A with r vector, let us say this angle is alpha. So this tan alpha will be equals to tan theta by 2. Got it? So now let us see some of the illustrations based on the same concept. Electric field at point P due to electric dipole is E. An electric field at point R on the equatorial line will be E by X. Then the value of X is. Okay, right, let us see. So we have given an electric dipole which is having an electric dipole moment Q times. Okay, let me take this in terms of P only, right? So electric dipole moment is P. So electric field at P will be 2 Kp by r cube, and the electric field at R will be in the direction, in the left direction. So let me call this as ER. So ER will be Kp divided by R cube, and R in this case is 2R, so it will be 2R cube, so it will be Kp upon 8R cube. So if I multiply and divide by 2, so we'll get 1 upon 16 2 Kp by R cube, and this is nothing but the electric field at P. So electric field at P by 16 will give us electric field at R. So we have to find the electric field by at R. It will be E by X. So it will be E by 16. So X comes out to be 16, right? So 16 is the answer of this question. Let us another question. The electric field due to a short dipole at a large distance r from the center of the dipole on the equatorial plane, whereas with the distance s, as you've seen, the formula is Kp by r cube. So option 3 is the right answer. Now let us the next problem type. It is the force experienced by a dipole in external electric field. So an electric dipole is placed on x-axis in proximity to a line charge of linear charge density 3 into 10 raised to power minus 6 coulomb per meter. Line charge is placed on z-axis, and positive and negative charge of the dipole is at a distance 10 millimeters and 12 millimeters from the origin. So what we have given, there is an infinite line charge, and this infinite line charge is on the z-axis. So this is x. Let me take this as the x-axis. Let me change it. So this is X, this is Y, and this will be Z axis. And a dipole is placed such that the positive charge is at a distance. So this is plus Q and this is minus Q. So minus Q is at a distance of 12 millimeter and plus Q is at a distance of 10 millimeters. So we have to find, and the force experienced by the dipole is 4 Newton. Find out the amount of positive or negative charge on the dipole. Okay, now let us draw the free body diagram. Now we have a positive line charge. So due to this positive line charge, the field will be along positive x direction, right? So that is the direction of electric field. So the force on the positive charge will be in the direction of electric field. Let me call this as QE1. And the force on the negative charge will be opposite to the direction of electric field. So that will be Q times E2. Since positive charge is closer to the line charge, the force experienced by that charge will be stronger. So we can say the net force will be QE1 minus E2. And force is given as 40 Newton. 4 Newton. And Q is, and we have to find Q. An electric field due to a line charge is given by lambda upon 2 pi epsilon naught times r. So it will be lambda upon 2 pi epsilon will be common, and then we have 1 by r1 minus 1 by r2. So 4 is equals to Q. Lambda is given as 3 into 10 raised to power minus 6 divided by, so if I multiply it with 2 and divide by 2, so this it becomes 4 pi epsilon naught, so it will be 9 into 10 raised to power 9 times 1 by r1. r1 is 10, so it will be 10 minus 1 by 12, and this is in millimeters, so we can multiply this with 10 raised to power minus 3 to convert that into meters. So let us simplify. So this will give us 2, and so 2 is equals to 27 into 10 raised to power 6 times Q, and the LCM will be 60. So 6 minus 5, so this will be 20 and this will be 9. So Q comes out to be 40 by 9. So Q will be 40 by 9 40 by 9 in microcoulomb. So that comes out to be 4.44 microcoulomb. So if you look at the options, option 4 is the right answer. Right, so let us see the next problem time. It is the torque experienced by a dipole in uniform external electric field. Two charges minus 4 microcoulomb plus 4 microcoulomb are placed at point A and B. A is 1, 0, 4, B is 2, minus 1, 5, located in the electric field E, which is 0.2 I cap. The magnitude of the torque acting on the dipole is 8 times root alpha times 10 raised to power minus 5 Newton meter, where alpha is. So we know what is the torque, right? So torque experienced by the dipole in external field, uniform field, is P cross A. So we need to find what is P vector. Electric field is given to us, and the negative charge is placed at A and the positive is at B. So we can say the electric dipole moment will be what is AB? First let us find AB vector, right? AB vector is 2 minus 1 I cap plus minus 1 J cap plus 5 minus 4 K cap. So this will be I cap minus J cap plus K cap. So unit vector in the direction of AB will be given as AB vector divided by its magnitude. So so I cap minus j cap plus k cap divided by root 3. So that is the direction. So we can say the dipole moment will be 4 micro, that is the charge, times the length of AB. So length of AB is root 3 and its direction is I cap minus j cap plus k cap by root 3. So that is the electric electric dipole moment. Now we have electric dipole in unit vector notation. Now we can apply the formula, right? So P vector is this, electric field is 0.2 volt per centimeter. So first convert that into SI units. So it comes out to be 20, so 20 I cap volt per meters. So torque will be P cross E. So it will so this is 4 micro and this is 20, so we can say it will be 80 micro I cap minus j cap plus k cap cross with I cap. So it will be 80 micro times I cross I is 0 and j cross I is minus k, so that will be k cap, and k cross I will be j plus j cap. And we want to find the magnitude. So the magnitude of the torque will be 80 micro times root 2. So which is nothing but 8 into 10 raised to power minus 5 root 2. So if we compare our final result with the given expression, alpha comes out to be 2, right? So 2 is the answer of this question. Right, so now let us see the next problem type, which is based on the potential energy of a dipole in external uniform electric field. An electric dipole of dipole moment 6 into 10 raised to power minus 6 coulomb meter placed in a uniform electric field. So we have given electric field and dipole moment is also given to us in such a way that the dipole moment is along the electric field. So this is P vector. Electric field is also in the same direction. The work done in rotating the dipole by 180 degree in this field will be, okay, so the potential energy is given by minus PE cos theta, where theta is the angle between the dipole moment and the electric field vector, and work done by the external agent is defined as the change in the potential energy. So U final minus U initial. So when we rotate the dipole by an angle of 180 degree, the angle between the dipole and the electric field will become 180, right? So the final potential energy will be minus PE cos 180, and the initial potential energy is minus PE cos 0 degree. So it comes out to be PE will be constant and cos 180 is negative 1. So 1 plus 1. So it comes out to be 2 times PE. So let us put the values. 2 times 6 into 10 raised to power minus 6 times 1.5 into 10 raised to power 3. So it will be 18 into 10 raised to power minus 3. So 18 millijoules. So 18 is the answer, right? Now let us see the last problem type, like simple harmonic motion problems in electrostatics. Let us see an illustration. So two electrons each are fixed at a distance 2d. A third charge proton placed at the midpoint is displaced slightly by a distance x, where x is very small in comparison to d, perpendicular to the line of the two fixed charges. Proton will execute simple harmonic motion having angular frequency. So we have to find the angular frequency. So let me first draw the situation. So we have given two electrons which are fixed, and there is a proton at the center. So in this very instant, in this situation, in this configuration, the proton is not experiencing any force. So this is so the proton will be in equilibrium. Now we have displaced the proton so slightly in the upward direction, right? And this displacement is x, and this x is very small in comparison to d. So this distance is d, this is also d. Now let us see what are the forces exerted by the electrons on the proton. So there will be a force of attraction by the left electron, Let me call this as F1, and there is a force of attraction by the right electron. Let me call this as F2, and this F1 and F2 will be having the same magnitude. So F1 is equals to F2, and it will be K E square divided by square of the distance between the charges, and the square of that will be x square plus d square. So we got the force. Now we have two force, and now we have to find the resultant of these two forces, and the resultant will be 2F1 cos theta. Let us, this angle is theta, this angle is also theta, right? So that is the resultant of these two forces, and it comes out to be towards the mean position. So the proton, so there will be a restoring force which will try to bring this proton back to its mean position. So let us put the value, and cos theta by trigonometry will be base upon hypotenuse. Base in this case will be x, and the hypotenuse is root of x square plus d square. So let us put the values. So 2 k e square, and cos theta is x upon, so this will become x square plus d square raised to power 3 by 2. Got it? Now x is very small in comparison to d. So x square is even smaller than d square. So x square plus d square can be written as d square. So if we use this approximation, the net force or the restoring force will become 2k e square x divided by d cube. So let us replace k, let us write k in terms of epsilon naught. So it will become 4 pi epsilon naught. And this force is opposite to the displacement, so I can say the restoring force will be negative of 2 e square upon 4 pi epsilon naught times d cube times x, right? And this restoring force can be written as mass times the acceleration. So acceleration will be minus 2 e square upon 4 pi epsilon naught m d cube. Right, so this is the equation of simple harmonic motion, where this vector is nothing but the square of the angular frequency, and we have to find the angular frequency. So root of this will be the answer. So root of this will be, so we have e square upon 2 pi epsilon naught md cube. So e square upon 2 pi epsilon md cube raised to power 1 by 2. So option 3 is the right answer. Okay, so this is the square of the angular frequency. Right, so I have covered all important problem types which can be asked in JEE Mains, and if you go through this video till very end, you have the idea what type of question going to come in exam.